Hey guys, today we're going to be taking a look at what's called the binomial theorem, and this is going to be using what's called Pascal's triangle. And what this is going to do is anytime we have a binomial that's raised to a power, we can easily work this out without actually having to do all of the steps to multiply all of the binomials together. Alright, now if you remember here, when we have these, first off, they're called binomials because they're two things. If I have a plus b squared, this is the same thing as a plus b times by a plus b. The squared tells us that there's two of them that are exactly the same, that are just multiplied together. If I had a plus b to the third, I would have three of them, and if I had a plus b to the fourth, I would have four of them. Now, if we were to actually multiply this out, I would get a squared plus 2ab plus b squared. And if you want to go ahead and multiply that out yourself to verify that it works, you can do that. But trust me, if you multiply those two together, we get a squared plus 2ab plus b squared. Now if I have three binomials together, and I want to multiply these together, I end up with a to the third power plus 3a squared b plus 3a to the second, 3a b to the second, and then b to the fourth. Sorry, b to the third, not b to the fourth. I'm getting a little ahead of myself. That'll be on the last one here. So for the last one here, we would have four of these all multiplied. And if we were to actually multiply these out, we would end up with a to the fourth. Hopefully you're noticing a pattern here. Plus 4a to the third, b to the first, plus 6a to the second, b to the second, plus 4a to the first, b to the third, and lastly, plus b to the fourth. So there's a couple of different things hopefully you're noticing here. First off, as we're going down the polynomials, the powers of a are getting smaller. So we started with a to the second, then a to the first, and then it's gone, so that's the same as a to the zero power. And secondly, the powers of b are getting bigger. We don't have a b here, so that counts as b to the zero power. Then we have b to the first and b to the second. And it's the same for all three of these. You see the powers are decreasing for a, and they're increasing for b. So we've got 0, 1, 2, and 3 for our powers of b, and it's the same thing here with this last one. This is one of the first properties of when we are expanding binomials. The powers of whatever comes first are going to decrease, starting with whatever our power is outside, and the powers of the second thing are going to increase, ending with whatever power is on outside. Now, the numbers that we see in front here, the coefficients, we get that from what we call Pascal's triangle. So let's take a look at Pascal's triangle. All right, Pascal's triangle right now just has three numbers here. We've got 1, 1, and 1, so that doesn't really seem to help us very much. But what this counts as is this first line counts as if we have a zero power. that would be our coefficient. Well, anything to the 0 power is always 1. Now, if we have a power of 1, that counts as just not multiplying by anything. That just counts as what we have. So we have a coefficient of 1 for both of our two terms. Now, if we expand it out, let's say we're looking back at our first example there, where we had a plus b squared. Our coefficients are going to be 1, 2, and 1. If we look at the second example I had, where I had a plus b to the third power, I would have 1, 3, 3, and 1. Continuing, the last example I showed you, we had 1, 4, 6, 4, 1 for our coefficients. Hopefully you're starting to notice a pattern here. If I take the two numbers that are right above and I add them together, I get what's down below. So 1 plus 1 gives me 2. 1 plus 2 gives me 3 for both of these 3's right here. 1 plus 3 gives me 4. 3 plus 3 gives me 6. And then 3 plus 1 gives me 4. We just keep adding 1s on the outside. So if I wanted to go to the 5th power, my coefficients would be 1, 5, 10, 10, 5, and 1. And I can go on forever this way. Does that make sense? Hopefully it does. When we're working problems, oftentimes it's helpful to draw this out yourself on your sheet, because you may have several different problems that you're going to be working that are going to require you to find different coefficients. For now, we're just going to take a look at one example. So I want to expand x plus 3 to the 5th power. Now, if you remember, when we drew out our triangle just a moment ago, the coefficients we had were 1, 5, 10, 10, 5, and 1. These are going to be the coefficients that I'm going to use in that next problem here. So I'm going to rewrite these numbers over on the next slide. One, 5, 10, 10, 5, and 1. I'm asked to expand this here, and so what I need to do is I just need to start with whatever I have first, raised to the highest power. So that's going to be x raised to the 5th power. Make that a little darker. So I just have whatever I have first raised to the highest power. That's got a coefficient of 1 right here, so I don't need to write it. So then I'm just going to go down the line. I'm going to have a plus sign. My coefficient's now going to be 5. I'm going to have the first thing raised to 1 less power. So I'm going to subtract 1 from my power here. So I'm going to have x to the 4th power now. Then I'm going to have the second thing here, the 3, raised to the raised to the 1st power. I'm going to keep going down the line. Now I've got a coefficient of 10. I'm going to subtract 1 from my power for the first thing, so I'm going to have x to the 3rd power now. And then now I'm going to raise the power of 3 by 1, so I'm going to have 3 to the 2nd power. I'm going to have to go 2 lines here because I'm going to have need more space. So once again, my 4th coefficient is going to be 10. I'm now going to have x to the 2nd power, because I'm going to decrease this power by 1, and 3 to the 3rd power. Moving on down the line here. I ran out of room. This still should all be one step. So then I will have a coefficient of 5. X will now be to the 1st power, and 3 will be to the 4th power. And then lastly, we will have a coefficient of 1, so we don't need to write that. The x is going to go to a 0 power, so that's going to go away, and we will simply have 3 to the 5th power. So now I want to do a little bit of simplifying with this because we don't want to leave the answer quite like this. This is a little bit messy. The x to the fifth, nothing to simplify there, so we can just rewrite it. We want to simplify this here. 3 to the first power is just 3, and then 3 times by 5 is 15. The x to the 4 will stay the same. So now this is going to be 15x to the 4. The next term over here, we have 3 to the second power, that's 9, and then 9 times 10 is 90, so I'll have plus 90x to the 3. Over here, we have 3 to the third power, that's 27, times by 10 is 270, x to the second. Over here, 3 to the fourth power should be 81, and 81 times by 5 would give me 170. If I did that correct, please check my work on that one. I did try and do that in my head. If we have 100, we should have 170x to the first. And as I run out of room here, this is a 170, it's just a little small. 3 to the fifth power should be 243. Once again, double check my work on that one. So this whole thing would be the expanded version of x plus 3 to the fifth power.